All right, welcome to the Explainer. Today, we're jumping into the chemistry of one of the most fundamental and versatile families in the entire organic world: alcohols, phenols, and ethers. I mean, these compounds are literally everywhere, from the fuel in our cars to the medicine in our cabinets. We're about to find out what makes them tick. So, let's get started. So, to get us started, here's a little riddle for you. What could possibly be the link between the disinfectant in your first aid kit, some high-performance biofuel, and one of the most common pain relievers on the planet? I know, they seem totally unrelated, but they all share a secret chemical identity.
And the answer is, they all belong to a single, incredibly powerful family of chemicals. And the tie that binds them all together? It's that humble but mighty carbon-oxygen single bond. That one connection is the foundation for a wild diversity of substances.
Okay, so let's formally meet the members of this family. They're all built around that same carbon-oxygen bond, but with some really crucial differences. We're going to treat this like a character study, getting to know each of their unique structures and, you could say, their personalities. Here they are, our three main characters. First up, alcohols. They have a hydroxyl group, that's an OH, attached to a standard carbon chain, which chemists just shorthand as R. Then you've got phenols. They also have that OH group, but it's attached directly to a special, super stable structure called an aromatic ring, so we label that R. And finally, ethers. With them, the oxygen atom acts like a bridge between two of these carbon groups. So you see, there's a clear family resemblance, but as we're about to find out, where that oxygen is attached makes all the difference in the world. You know, even their shapes tell a story. The bond angle in an alcohol like methanol is about 108.9 degrees, and that's because it gets squeezed a bit by the invisible electron pairs on the oxygen. But in an ether, that angle opens up to over 111 degrees. Why? Because the two bulky carbon groups are literally pushing each other away. We call that steric repulsion. These tiny little shifts in geometry are the first clue to their very different personalities. Now that we've seen their basic structures, let's explore their physical personalities. We're going to see how those subtle differences in shape lead to one particular trait that gives some of them what I like to call a chemical superpower. And that superpower is intermolecular hydrogen bonding. Honestly, the best way to think of it is as molecular handholding. The slightly positive hydrogen of one alcohol molecule gets really attracted to the slightly negative oxygen of a neighbor. This attraction holds all the molecules together, which means you need a lot more energy, a higher temperature, to pull them apart and turn them into a gas. Ethers, well, they're missing that specific hydrogen, so they just can't do this. And this chart just illustrates the effect perfectly. Take a look. Ethanol, which can hydrogen bond, has a boiling point of 78 degrees Celsius. Now, diethyl ether has a similar mass, but it can't H-bond, and its boiling point plummets to 34.6 degrees. And a hydrocarbon of similar size, it boils below freezing. That's the power of that molecular handholding right there. We can see a really fascinating version of this in these two molecules. Para-nitrophenol, it holds hands with its neighbors, that's intermolecular bonding, creating these strong networks that give it a high boiling point. But orthonitrophenol is different. It's kind of introverted. It folds in on itself and forms an internal hydrogen bond. It holds its own hand. And because it's not connecting with its neighbors, it's way easier to vaporize, which makes it steam volatile, a classic separation trick. Okay, so we know what they look like and how they behave physically. Now let's get into the action, their signature chemical reactions and transformations. This is where things get really interesting. So here's one of the biggest questions in this family's chemistry. Why is phenol so much more acidic? Why is it so much more willing to just give up its proton compared to a typical alcohol? I mean, they both have that OH group, so what's the deal? The answer, in one word, is stability. When an alcohol loses its proton, it forms this unstable ion, where the negative charge is just stuck on the oxygen. But when phenol does the same thing, it forms something called the phenoxide ion. And this ion is incredibly stable. Why? Because that negative charge isn't trapped. It gets shared and spread out across the entire aromatic ring through a process called resonance. And a stable product means the reaction is way more likely to happen in the first place. You know, chemistry is all about conditions. Take the dehydration of ethanol with sulfuric acid. If you crank the temperature up to 443 Kelvin, the reaction favors elimination, and poof, you get ethene, an alkene. But if you just drop the temperature by 30 degrees, down to 413 Kelvin, the entire mechanism switches to substitution, and you end up producing diethyl ether instead. A tiny change in temperature, a completely different outcome. All right, let's look at another classic chemical puzzle. When you react an ether with hydrogen iodide, you basically split the molecule in two. But the big question is, which piece does the iodide attach to? It's not random at all. There's a clear logic to it, and we can figure it out. And here's the logic. It's like a decision tree. First, you ask yourself, is one of the carbon groups a tertiary carbon? Meaning, is it bonded to 3 other carbons? If the answer is yes, the iodide attacks that spot because it can form a super stable positively charged intermediate called a carbocation. But if the answer is no, the reaction takes a different path entirely, and the iodide attacks the smaller, less crowded carbon group. It's just a beautiful logical process. Now, of course, this isn't just a bunch of abstract theory. Let's connect this chemistry directly to the world around us, from the gas pump all the way to the pharmacy. The impact of this chemical family is just enormous. Ethanol gets blended with gasoline to create gasohol, a cleaner burning biofuel. Derivatives of phenol are powerful antiseptics used in disinfectants. Both alcohols and ethers are absolute workhorse solvents in countless industrial processes. And, of course, they are central to making all sorts of pharmaceuticals. A perfect example is making aspirin. You start with salicylic acid, which is pretty cool because it's both a phenol and a carboxylic acid. By reacting its phenol group with something called acetic anhydride, you do what's called an acetylation reaction, and that produces acetylsalicylic acid, which is just the fancy chemical name for aspirin. A simple, elegant reaction that has probably relieved billions of headaches. So, what if you're in the lab and you've got an unlabeled bottle? How do you figure out which family member you're dealing with? Well, it's time to pull out the Chemical Detective's Toolkit. Here are a few simple visual tests you can do. Because phenols are acidic, they'll turn blue litmus paper red, while neutral alcohols won't do a thing. If you add a few drops of ferric chloride, phenols give you this really distinct violet color. Or add bromine water, and phenols will react to form a white precipitate. Alcohols, they give no reaction in those last 2 tests. It's a dead giveaway. But what if you already know you have an alcohol, and you just want to know what type it is? For that, we use the Lucas test. You add the Lucas reagent, and a cloudy haze appears as the alcohol reacts. Now here's the cool part. A tertiary alcohol reacts instantly. A secondary alcohol takes about 5 minutes. And a primary alcohol? It won't react at all at room temperature. The speed literally tells you the structure. Another really powerful tool is the iodoform test. If you get a positive result, this bright yellow precipitate forms. It's super specific. It tells you that the molecule has this exact structural unit, a methyl group attached to a carbon that's also holding a hydroxyl group. So ethanol will give a positive test, but its close cousin methanol won't. It's a great way to tell them apart. So let's wrap up with the key takeaways from all this. First, we saw again and again how a molecule's structure dictates its physical properties, especially with that hydrogen bonding superpower. Second, we learned that resonance is the secret sauce behind phenol's unique acidity and reactivity. And third, we discovered that reaction outcomes are never guaranteed. They depend so critically on the specific conditions and reagents you decide to use. In the end, just memorizing reactions, well, that's only the what. It's only the first step. The real story, the really fascinating part, is always in the why. It's about understanding the hidden forces pulling the strings behind the scenes. So next time you look at any chemical transformation, I hope you'll ask yourself, what's the secret story of stability, structure, and energy that's really making this all happen?